How's your Thanksgiving?
It's great.
weekend?
Yours? I mean, not great, but I mean, considering it was family stuff, you know, as fun as that could be. It was nice. Yours?
It was nice until I had to go to work. Black Friday.
Yeah, that's fun. Okay, y'all ready? So solving a system of equations, we did last class 2 equations, 2 unknowns. We talked about how that represented geometrically the intersection of 2 lines, right? That's what we were talking about. And then we talked about 3-dimensional space, 3 equations, 3 unknowns. What does it even look like? And what did we say 3 equations and 3 unknowns represents?
Matrix or not matrix, but 3-dimensional space.
Yes, but as far as what do they look like? They just look like planes, right? So you're trying to figure out where these planes hit each other, right? So let me give you a system of 3 equations and 3 unknowns. Let's see. Let's use, I guess I'll use one of their examples to keep our numbers nice. X plus y minus z equals -1. -7y plus 6z equals 20. And then y, or you know what, let's make it z equals 1. I want you to look at this and first recognize that you do have 3 equations. Do you have 3 equations?
Yeah.
Okay. Are there 3 variables within the equations?
Yes.
Well, the first equation you have x, y, and z, don't you? Equals -1. The second equation doesn't have an x there that we can visually see, right? But there is actually an x out here, if we just imagine it being a 0x, right? So then it does have x, y, and z, doesn't it? And then the next one, same thing. 0x, 0y, plus what, 1z? So they all do have x, y, and z in them in some fashion, yes? All right, now, what I do want you to notice is that the last equation already tells us what z is, doesn't it?
Yes.
Z is 1. So if I know that z is 1, can I figure out what y is? By doing what?
Substitution.
Plugging this value of z back in here, right? So everyone agree with that? I could get y by just replacing z with 1 here. Then once I have y, could I get what x is? Yes, because I know what z is and I know what y is. Yes? I'm going to do it right now, but I just want you to see, I'm going to erase these, that when we get a system of equations with 3 equations and 3 unknowns, our goal is to make it look like this. Because if we can make it look like this, it's easy to solve. Right? So notice, you can almost imagine there's like nothing below the x's, right? And then below the y, these 2 y's, it's blank. Then you have a z by itself. If we can get a matrix, or I'm sorry, a system of equations with 3 variables and 3 unknowns to look like this, we're in business. All right? So let me start doing what's called the back substitute stage. I call that the BS stage, right? We're going to back substitute. I'm using the fact that z is 1, right? And going to the second equation, which I'm going to say, I'm going to start writing this down. Equation 2 is the second equation, is -7y plus 6z equals 20. And now replace z with 1. So -7y plus 6 times 1 is 6. And then now you have an equation with just y in it, so just move things around. What do you get? Y is what? -2. So I'm assuming everyone here can solve that. All right? So now that I know what y is, I'm going to go and look at which equation? Equation 1 now, right? I'm going to look at equation 1. I'll write that down up here. Equation 1 is the equation x plus y minus z equals -1. And replace z with 1 and y with -2. So x plus -2 minus 1 equals -1. Do y'all see what I'm doing? Okay, and then just figure out what that is. What's this? X minus 3 equals -1. So x is what? 2. And so you know what x, y, and z are, right? And we're going to write them down. Remember when we had 2 equations and 2 unknowns, we wrote them down as an ordered pair, like x, y, z? X, y, yes? Now what we're going to do is we're going to write these in order also, but we don't call this an ordered pair. Let's see, 2y was -2 and z was 1, wasn't it? So x, y, and z like this. We don't call this an ordered pair, we call it an ordered, anyone know? Triple. An ordered triple. Now, this means that we had 3 planes, right? 3 flat sheets of paper oriented in 3-dimensional space. And they all intersected at a single point. So this would have been, the analogy here would have been when we were looking at this wall as being a plane, and this wall as being a plane, the roof as being a plane, then the intersection would be that point in the corner of the room. That's the case that we have here, all right? Everyone understand this? All right, now I gave it to you in a very nice format. Now what I'm going to do, I'm going to give you this same problem, but before we got to here. Because again, this is the goal, to get it to this. How do we get it to look like this? So let's take a look at this problem in its original format. Would everyone agree that once we got to the back substitution, it was pretty clean? Everything just gets plugged in? Okay. It's getting there which presents the challenge for us. So here's another system, or here's that same system, but not written all pretty for you. So that first equation hasn't changed. I have to really make sure I copy this down correctly, because if I don't, everything's going to be way off. I don't think I've talked to you about this because we haven't used z a lot, have we? Z has not come up a lot with us in this class. For those of you, which most of you are going to be taking more math and doing more math in your life, I used to not strike my z's. When I used to write z's, I would just write them like that. And eventually, I decided, you know what, I better start striking my z's so that I can distinguish them from my 2's. I recommend you do the same thing. They do, right? So that's why I strike them. It's just a little bit of, FYI, if you want to do it, it's a good habit to pick up. Another thing you might want to pick up is when you write the letter T, I curl my T's at the bottom so I don't confuse them with pluses. Little things like that can get you in trouble later, especially if someone's trying to read your work. All right, you ready? That looks nothing like what we just had, does it? The first equation is still the same, right? The second equation is not, third equation is not. Now they all have x, y, and z in them. Somehow, some way, we need to make this look like what we just did. All right? So eventually we're going to get a z equals 1 down here, right? Yes? So the way I'm going to do this is I'm going to use the things that we're allowed to do when it comes to a system of equations. And remember I told you about the kid Gauss that did that thing in adding the numbers, right? I talked about that last class. And that this is actually called Gaussian elimination. The things you're allowed to do when you have a system of equations is you can always multiply any equation by any number. We kind of knew that already, right? Multiply this equation by 2 if we want, and this equation by 5, it doesn't matter. You can also add any 2 equations together. Any 2 equations, you can add them together and replace any equation with that answer. So let me just give you an example. If I wanted to take equation 1 and add it to equation 2, I'm allowed to do that. That's going to give me a new equation, right? that answer can replace equation 1 or equation 2. I'm allowed to do that. All right? That's one of the rules that we're allowed to use with elimination. So you can add any two equations together and take that answer and replace any of those equations with it. Okay. And that's pretty much it. So let's go ahead and try and make this happen. All right? So going back and looking at what we had earlier in the problem I put up before, right? X plus y minus z equals -1. I told you to pay attention to the fact that we had nothing underneath that x, right? Everything below the x was gone. So what I'm going to try and do is try and get rid of these two and make them go away. Yes? You want to multiply the bottom equation by -2? Everyone agree we could do that? And that would make this a -4? And then I'm guessing you're going to add those two together? Yeah, okay. I have no problem with that. Everyone agree? We can do that? Now look, there's not one way to do this. There are many ways to do this, all right? I'm just going to go with, as long as it's legal, legitimate, I'll do it, all right? So let's write down kind of in words what we're doing also. I'm taking equation 2, right? Equation 3, and I'm multiplying it by -2. So I'm taking -2 times equation 3. That's what I'm about to do? All right. So let's go ahead and rewrite the whole system. I know you're not going to like rewriting this over and over and over, but get used to it. Your hand's going to hurt, maybe. So now, what do we have here? -4x plus 4y plus 6z equals -10. So just make sure you pass the -2 through the entire equation, both sides. And now, what do you want to do? Add them together. So you're going to take this right now, right? What we just found, and we're going to add it to what? Equation 2. So we have to kind of agree on what we're doing here. See, this system of equations, this was equation 3, right? I multiplied it by -2. Does everyone now agree that we'll call this equation 1, equation 2, and equation 3? So this is a new equation 3 now. It's not this one. It's this one. So I'm going to take equation 3 right now, and I'm going to add it to equation 2. That makes sense? And I can take that answer and I can replace either equation with it. So which equation would you like me to replace? You want to go 3? I heard 3. Let's go with 3. Equation 3. So that's what the arrow means. I'm going to add equation 3 and 2 together and then replace, that answer is going to replace equation 3. So let's try and write this now. I have x plus y minus z equals -1. I have 4x minus 3y plus 2z equals 16. And then you add the two together. So what happens when we add these two equations? No x's, right? That's what you wanted, right? How many y's are we going to have? 1 y. Z's? 8 z's equals 6. Okay. Now, we're just partially there, right? We have nothing here, which is nice. Now we need nothing here. How we can get rid of this one?
You can't multiply by 0.
Can't multiply by 0. I mean, you can, but then you eliminate the equation. Top equation by -4? That okay with you? Yeah. Right? If we do top equation by -4, we'll get these x's to go away, right? So that's what I'm doing. I'm writing down my steps here. I'm going to go -4 times equation 1 now. This is just to keep track of everything I'm doing, just so you can see it, all right? All right, so now I'm going to rewrite a new system. My new system is going to look like the top equation is going to be negative 4x minus 4y plus 4z and then equals positive 4. Everyone agree with that? That's negative 4 across the top equation. The bottom the second equation is still 4x minus 3y plus 2z equals 16. And then the third equation is still y plus 8z equals 6. So I will now add equation 1 and 2 together and replace 2 with that. So I'm going to take equation 1, add it to equation 2, and replace equation 2 with that. See what I'm saying? You wind up with like a sheet full of all these systems of equations when you're done here. Does anyone have any questions on my notation over here? Or? All right, so I add these together, right? That's going to become my new equation 2. But what about equation 1? Just leave it the same? Okay. Negative 4x minus 4y plus 4z equals 4. And then my new second equation is negative 7y plus 6z equals 20. And then my third equation was still y plus 8z equals 6. So you have this. One more thing to do. Yes?
Multiply the bottom equation, or the top one, by negative 1. Yeah, take out all the y's.
So you're trying to get rid of the y's, right?
Yes.
We want to free this up, right? We want to get nothing here so that all we have is z as a number, right? And we're hoping it'll say z is 1, right? So we want to get rid of these y's right here.
So we end up with a negative 1 somehow with two of those together, right?
Well, let's see. How can you make this y go away? Multiply this bottom row or bottom equation by 7. Look, take a 7 out here, and what's that going to do with my y's? It's going to cancel them out, okay? So I'm now going to do 7 times equation 3. And I'm going to rewrite the whole thing again. And then, let's see, 7y, what's that, 8 and 7? 56. Z equals 42. Yeah? We good? Now what do you want me to do?
Equation 2 and 3.
Add equation 2 and 3 together. And replace what with that? 3. So you rewrite the whole system again, right? Which is this. But that last equation, instead of being that, is going to be what? Add these two together. 62z equals 62. Do y'all see it? Here to here? You're adding. This and this, they go away, right? And then this and this, that's 62 z's, and then this is 62. But your first equation's not going to change.
Wait, so why do you still have the negative 7?
I didn't do anything to this row. Remember, Remember, what we're allowed to do is we can add any two rows together and replace one of them with the answer. The other row doesn't get changed. It stays exactly the way it was. Okay, now, we have reached the goal that we wanted. Okay, the goal was to get it where it was nothing here, right, below the x's. There was one space below the y, and it was just z by itself equals a number. And we have that, don't we? Now we can figure out what z is. Yes?
Are you able to like factor out a 4 on the first one?
Yeah, now, remember, if you go back to the problem I gave you before this was not -4, right? It didn't look like this because we came in here and we tweaked it, right? We multiplied by -4. Couldn't I just divide by -4 now? And I'd be right back where I was? But I don't need to. I can just, from here, I can just go back. So this would be our back substitution step. Look, do your back substitution at this point. So start out with equation 3, which says that 62z equals 62. I think we all agree there, dividing both sides by 62, we get z is 1, which is what we were hoping for, right? And then now you go to equation 2. Equation 2, -7y plus 6z equals 20. Replace this with 1, right? You get -7y plus 6 equals 20. So you get y was -2. Was that what it was earlier? Yes?
Oh, never mind.
So move the 6 over, it's 14, divide by -7, -2. And then now go back to equation 1, and you could do it here into this one, and you should get, what, x was what? 2? Okay?
So the main goal when we work this out is just to get that z to 1. We don't have to worry about anything else.
The goal when you have a system of 3 equations and 3 unknowns, the goal would be to get one equation that has maybe x, y, and z in it. Underneath it, nothing, no x's. And then the next equation, just y and z in it, with nothing below it, and the y's, and then the z's by itself. If you want,
that pattern.
that's right, you want that pattern. Now, it doesn't really matter when you have this system. You could have x's, y's, z's, y's, z's, and then z's. Number. I don't know if this makes sense. You have some, like maybe it's like 2x minus 3y plus 5z equals 10. And then the next one is just y and z in a number, and the last one is z in a number. That's what we're hoping for, because we can always go back from here, right? This number into here, that will get y, and then both y and z in here, we got x. So there's almost like this, this blank triangle underneath there, where there's really like a 0 here, and a 0 here, and a 0 here. Remember, like 0x, 0x, 0y right there? Understand?
Yes, sir.
Okay. Everyone see that? Okay. All right, now, with that in mind, there are situations where you could get no solution, just like we had with lines. Remember, if the two lines were parallel, you get no solution. If the two lines were on top of each other, you got an infinite number of solutions. You can have that happen here also, but I'm not going to go through that just because of time, all right? If a system of equations has an answer, it's called a consistent system of equations. If a system of equations does not have an answer, no solution, it's called inconsistent. And the book talks about that too. All right, so let's take a look at a nice example, all right? I'm wondering if I should make this problem up, or if I'll just use the one in the book. I'm going to give you 3 points. -1, -4. That's a -4. 1, 6, and 3, 0. All right, these are points, all right? And I'm going to plot them for you real quick on a graph, 2-dimensional. -1, -4. The next one is 1, 6. It's here. And the last one is 3, 0. Now, let's talk about something before we get into this problem. How many points do you need to define a line? 2 points. Everyone agree? If I give you 1 point by itself, there's an infinite number of lines that goes through 1 point, right? But if I give you 2 points, there is only 1 line that goes through 2 points. Yeah? So given 2 distinct points, there is only 1 line defined between the 2. If I give you 3 points, there is only 1 parabola that goes through those 3 points. Remember parabolas, right? Okay? So I'm giving you 3 points right now, and I'm telling you that they live on a parabola. I want to know the equation of that parabola. And I'm only giving you 3 points. Does everyone understand what I'm saying? Like, there is only one way to draw a parabola through these 3 points. There's only one you can draw. Just like the line thing. If I give you 2 points, there's only 1 line you can draw. If I give you 3 points, there's only 1 parabola you can draw. All right? Well, I don't know. We're about to find out. All right? I want to know now, what's the equation of this parabola? What is the equation of the parabola through these points? That's it. That's all I'm giving you. So let's think about this. What is it that we want to find? What is it we're trying to find? The equation of a parabola, right? That's what you want, the equation of a parabola. Can you tell me anything about the equation of a parabola? What does it look like? Tell me again. Y equals what? X. That's a very specific parabola. That's the one that opens up and is just sitting here at the origin, right? Can you give me the equation of a more general parabola?
A squared plus bx plus c.
You said that, yes, close. A x squared plus bx plus c. Now, if you go back in your notes, when we were studying parabolas, there were 2 forms for parabolas. There was standard form and then the expanded form, which was this one. And when we were graphing parabolas, we had different techniques as far as graphing them. If it was given to us like this, we did a certain thing. If it was given to us in the other form, this was the other form. Remember this one? I know it's been a long time.
Oh, that's the vertex.
That's the one where you can see the vertex already, right? So I know that what I need to give to whoever's asking this question, right, is I need to give them either this and this, or this, right? But if I'm going to give them the specific parabola, I'm going to have to determine in this problem what A is, what B is, and what C is. Do you agree? So I need to be able to find A, B, and C. I need to be able to find 3 things, right? 3 unknowns, 3 variables, right? But I'm also given 3 pieces of information. I know that when what this means, right, this point means, is that when I plug in -1 for x, the function spits out -4, doesn't it?
Yes.
When I plug in 1 for x, the function spits out 6. And when I plug in 3 for x, it spits out 0, yes? So let's now use each of those pieces of information, and I'm going to go with this one right here. I could go here, in which I would have to find A, H, and K, but I'm going to stick with this one, and this is the way you should do it if you're ever trying to find it. All right, so let's use first the first point, -1, -4. And remembering that the -1 is the x and the -4 is the y, right? What I want you to do is I want you to rewrite this equation right here. We don't know what a, b, and c are, right? But we know that when we plug in -1 for x, this y should be -4, right? That's what should happen. If that point lives on this parabola, then when I plug in -1 for x, it better spit out -4. So let's do it. I put, what, -4 on the left side equals a times -1 squared plus b times -1 plus c. You with me? Now, let's just clean that up a little bit. That's -4. -1 squared is just 1, so this is just a. This is minus b, because it's -1 times b, and plus c. I have one equation, right? 3 unknowns. One equation, 3 variables. Well, I'm going to be able to do this again, right? For this point. And I'll have another equation with 3 unknowns. And I'll do it for the last point, and I'll have a third equation with 3 unknowns. So then I'll have a system of equations, right? I'll have 3 equations, 3 unknowns. Okay, so now I'm going to box this up. I'll come back to it in a minute. I'm going to use 1, 6. So that means 6 comes out when I plug 1 in for x. So 6 equals a plus b plus c. It's my second equation. And now use the last point, which was 3, 0. And that means 0 comes out when I plug in 3 for x. Did y'all get this? Okay. What's my last equation look like? 0 equals 9a plus 3b plus c. There are my 3 equations. Right? So whatever my parabola is, we said that we had to figure out what a, b, and c were, right? That's what we had to figure out. What's a, what's b, what's c? And now I have 3 equations that give relationships between a, b, and c. So I should be able to set up a system, right? Now, which one of these equations do you want to put? Does it really even matter? I guess it doesn't matter which order these go in.
They don't need to be in the order though.
Nope, they can be in any order. Yep. So here's my system. Let's just put them in the order I found them in. And also, watch what I'm going to do. I'm going to rewrite this equation. A minus b plus c equals 9. So I did, sorry, 9. I don't know why I put 9. I meant to put -4.
I think it's A minus B.
That's this one, right?
Yeah.
And then the next one, a plus b plus c equals 6. And then last one, 9a plus 3b plus c equals 0. All right, you ready? What's that? The b's do cancel out. You could do it that way. There's a bunch of different ways to do these, but I'm trying to show you is more of a systematic approach. You know, there are ways that you can get in here, and you could add these two together, and then you'd have 2 equations, right? If we add these 2 together, the b's go away. So we have 2 equations with 2 unknowns up there. And then you could keep going. But I'm going to just try and do this little triangulation again and get basically this thing to happen, where these are gone. So -9, second equation, will make the 9a and the -9a go away, wouldn't they? Yes? So I'm going to see if I can work a little faster here. I'm not sure how this is going to go. Okay. A minus B plus C equals -4. I'm going to, well, I don't know how fast y'all want me to go. It's only our second example, so all right, -9A minus 9B minus 9C equals -54. And the third equation is still the same. Didn't change it. Now what? Add equation 2 and 3 together and replace 3 with it. Okay? I'm going to add these two together and make that my new third one. So next to this, I'm going to write and tell you what I'm doing. I'm doing equation 2 plus equation 3, and that's going to become my equation 3 in this new one right here. I'm taking.
You replace equation 2?
You don't have to. You can replace either one.
Okay.
Doesn't matter which one you replace. I'm just going to go with the bottom one. All right, so I have A minus B plus C equals -4. I have -9A minus 9B minus 9C equals -54. And then replacing the third equation when I add down, what is it going to be? -6B minus 8C equals -54. Any questions? Now, what would you like me to go after now? You want the first equation times 9? I agree. First equation times 9 will give me a 9A up there, and that'll kill off with this A. So I have 9A on top minus 9B plus 9C equals -36. My second row is still there, didn't change it. And my third row didn't change. I'll leave it. Add first and second equations together and make that my new second equation. So this one right here, this new second equation is my equation 1 plus equation 2 is now becoming my new equation 2 right here in this one. So what is it? -18b. Oh, the c's canceled. So equals what? -90. Is that what you? 90? And the last equation? Didn't change, right? Everyone with me? Okay. Well, that's what I'm about to ask you. Our goal is to try and get this little triangle thing to happen, right? That little diagonal, which means if you're just following that, the next thing you'd want to do is get rid of this, right? That's what you would want to do? But if you understand overall what you were really trying to do, you were trying to get z as a number, right? Once you knew z was a number, you could go back and you could get y, and then once you knew y, you could go back and get x from the y and z. Here we're using different variables, right, a, b, and c. I know what b is, don't I? If I know b, can I get c? Where? Third equation, right? If I know what b is, I can get c. So if I know b and c now, I can go back and get a. Can't I? All right, so at this point, I'm free to back substitute. You have to recognize that. So that's why I'm not trying to turn you all into monkeys here. I'm glad you saw that, because that's really what we're trying to see, is at what point can you start back substituting? If you get it to the triangle thing, you're there, no, you're guaranteed to be there.
We can make a triangle.
We could. We could go one more step, right?
Flip-flop the equation.
Flip-flop them, yep. But I'm going to do something to this system before I start back substituting. Let's see if you're okay with this. A minus B plus C equals -4. Does 18 go into 90?
Yes.
5 times, right? B is 5. And then this one, what, 2 goes into all those?
Oh, sorry.
Right? So I'm actually going to go 3B plus 4C equals 27. So what did I do here? Tell me what I did. I simplified. I took the first row, first equation, I divided everything by 9. Right? Because didn't I multiply by 9 earlier? And I made it look more complicated. So I divided back by 9. So I divided this row by 9 to go up there. Then this one, I divided both sides by what? 18? Sorry, divide this by 18. Then this one, I divided everything by -2, right? Because they were all negative, I want to make them all positive. That's a little easier, I think, to work with when we go and back substitute. Do you agree? We could? We didn't have to do that, but it just makes our numbers a little easier. That's all. So back substitute. B is 5. All right. I'm going to go to equation 3. 3B plus 4C equals 27. Replace B with 5. So you get 15 plus 4C equals 27. Subtract 15 on both sides. 4C is 12. C is 3. Now go to equation 1. A minus B plus C is -4. A, let's see, negative B is -5 plus C, C is 3 equals -4. So what's A here? -2. So you know what A, B, and C are?
You're only going to put one of these on the text.
Yeah, you would only get one. These take a little while, don't they? Yeah. And what if if you make one little mistake? I mean, it can really throw things off. So you have to be very meticulous. So remember, our equation that we were looking for the parabola looks like this. But we know now exactly -2x squared, what was B, 5? Plus 5x, and then plus 3. That parabola right here, if you graph it, will contain those 3 points. And that's the only parabola that would contain those 3 points. There is no other one. So here's what I'll promise you on the final, okay? When you run into these problems on the final, when you have a system of equations, 3 equations, 3 unknowns, I promise you integer answers, right? In other words, it'll be nice whole numbers. They could be negative, like 3, -2, 5. I promise you those. That way you know that if you get like C is 3/7, you know something's wrong, all right? And that way you can go back and check. Now, if it's 2 equations, 2 unknowns, I do not promise you integer answers. Those could be fractions, because that's what we did last class, right? All right. But if it's a system of 3 equations, 3 unknowns, if you get something other than integers, something's up, all right? This is actually called, it's a form of what we call curve fitting or regression modeling. You take real life situation, you take data, what we do is we try and fit a function to that data so that we can model it. One example that came to mind was a baseball player hits a ball, right? And we can kind of estimate the point at which the ball came off the bat, how high it was off the ground. We can somehow give like an x and y coordinate to that point. We know maybe where in the stands it's a home run, where in the stands it hit, so we have another point. And so all we need is one more point, right? So if we had, which we could do, we could somehow, you know, fix the camera to look at one specific region or something, and we could get some estimate for that third point. Then once we have that third point, we can calculate the actual parabola, right? And once we have the parabola, I can tell you how far it would have gone because I know the equation. And if I know the equation, I can find the x-intercept, right? And wouldn't that red point down here represent the x-intercept of this? So I just set that equal to 0 now, use quadratic formula, and I'd be able to figure out how far that ball would have gone had it not hit the stands. Understand? But I need 3 points to do it. Now, yeah. Sometimes don't they say, I'm not a big baseball fan, but I have seen, anyone watch baseball, like baseball? Yeah, like don't they say how far the home run was? Like even though it like hits way up in the stands, they'll say that would have gone so far. Yeah, sometimes, yeah. So.
I like the part where you take the 10-minute break to.
I know, how long does it take them to check it?
Oh, that's done instantaneously. Because, you know, this Gaussian elimination is perfectly suited for a computer. I told you this last class. I mean, what did we really do here? What were the operations? Adding, subtracting, multiplying. That's pretty much it, dividing. And a computer can do that really quick, right? So we have algorithms that we write that, you know, any computer science majors? Where are my computer science? So like even as a math major, I took a class called numerical analysis where we had to write up the code to do Gaussian elimination. And so we had to actually code up this process. And so you go in there and someone would put in a 30 by 30 system of equations. So 30 equations, 30 unknowns, and have your algorithm go through and solve and get the solution. But the computer can do it quick, super quick. And then what we did was we actually tried to find weaknesses in the code and exploit the weaknesses so that the computer would give us incorrect readings and incorrect answers. Basically, we'd make the computer round too much, and it would give us too much error. So, but what I'm getting at is that when on a computer, what would happen is they would just type in the 3 points, and it's like that. It's done. So why are we doing it by hand? Just for fun. Just for fun. That's a big question. Why do we do all this by hand?
Well, I know why you do it.
Why?
You get paid.
That's exactly right. No, this is a good debate to have. I mean, if you think of everything we've done in this class as far as like graphing functions, if we go to Wolfram Alpha and we just type it in, it's going to graph it. It's going to give us x-intercepts. It's going to do all that for us. So why? Do you have an answer? Or,
I don't know the answer, I'm just thinking.
okay, yeah, no, I want to hear opinions because there's no right answer, there's no wrong answer. Go ahead. What do you think?
Funny answer.
Oh, I was getting ready for that one.
But like, in all seriousness, I think a technological apocalypse is very likely to happen.
Okay.
So like, we have to have a basis for something in order to get by, just in case something crashes or something happens where we have to go back to living like, in a basis.
So like preppers, like we're going to be like, you know, whoa, fire. that far back? Go back to fire? Someone was asking me the other day what I thought the greatest human invention was, and I told them I thought it was fire. And they told me, that's not an invention because it was there before. I said, yeah, but when we actually got to control it, like figured out how to do it ourselves. And, okay, so yeah, I like that answer. I mean, I totally agree with this because to me, I like technology. I like the fact that computers can do a lot of this now for us. But there's got to be a balance. There's got to be some balance. You can't completely lose touch with the theory on how to do something because you get, in engineering, in a lot of fields that use computers to solve problems, they have what's called the black box theory. So you have this engineer that's trying to build a bridge, right? So they sit down at their computer, they type in the problem, right? And then they put it into the computer, and the computer spits out a solution, right? It does, yes, it does make noises like that sometimes, if the problem's good enough. So you've got a solution, right? Does that engineer trust that solution?
Yes.
Yes, absolutely. But does the engineer understand how this actually got to that answer? And that's what is dangerous. This is the black box, okay? That's the danger. If nobody understands the actual theory, then nobody understands why the code was written the way it is. You're trusting that, and you don't know whether, you truly don't know if it's correct or not. You're just trusting a computer and someone's algorithm, right? When I was in the end of my undergraduate degree, I took that class in numerical analysis, and our project at the end of the semester was we had to find 4 well-known, accepted mathematical programs used by mathematicians or engineers. We had to take these programs, we had to get into the code for any of the like built-in routines like Gaussian elimination or whatever it was. We had to get into the code of it, and we had to find a weakness in it, and we had to exploit it. And so what we did is we would get this problem, and what we would do is we would find the solution correctly, theoretically, like doing the rigorous, whatever it took to get to the correct answer. We knew we could prove with no doubt what the solution was. But because we knew the way the code was written, we would get this thing to spit out something that was wrong. And that was a project. We had to do it for 4 different programs. And so to prove the point that if you don't understand the theory behind something, and we get to a point where all we do is trust this, then when this goes away or this fails us, and we're so far removed from the theory that, like you said, you can't go back far enough, right? It's like, how do you make a wheel out of wood? Anyone know how to make a wheel out of wood? They used to have wooden wheels, right? Like, how do you make a wheel out of wood? That's a lost trade, right? There's probably only 5 people in the world that can still do it, right? I mean, now, do you need it? No, right? You don't need to make a wheel out of wood. But it's the same kind of concept. If we move too far away from the theory, then you're possibly get lost later. And then at the same time, I mean, there's deeper things here. Understanding, work ethic, blah, blah, blah. Shall we move on? Of course.
That was really interesting. We should continue on that.
Continue that conversation. Yes.
There was a show, though, on the technological apocalypse called Revolution. It's on Netflix.
What is it called?
Revolution.
Revolution? It's on Netflix?
Yeah.
It's a show or?
It's really good.
Okay. Well, I know what will happen to all the kids that I know that are like 18 and under. If all technology went away right now, they'd all fall over and start quivering on the ground. What am I going to do? Why my phone's not connecting anymore? All right, matrices.
Then it just turns into a
All right, matrices. Everything we've done up to this point, okay, with these systems of equations, it can become kind of tedious to write things over and over and over. So all that matrices are just another way of representing systems of equations. That's all it is. So let's just take this system. We'll start with this one. X plus y equals 10, and 3x minus y equals 10 again. All right, so what is a matrix? Well, what we do is we take the system, we realize that the only things that really matter to us are the numbers, right? Like, if I'm going to do this first thing of trying to get these x's to cancel, let's say, I would want to know, what this number is so I can multiply that top row by -3, right? To make the x's go away. Yes? So that number is really the only thing that's important. The fact that it's an x, well, I kind of know that already because the way it's written. So a shorthand notation for this would be to write it like this. Instead of a brace, we use a bracket. And all we do is we write the coefficients, just the numbers. So the coefficient in front of x here is 1. The coefficient in front of y here is 1. And then the number over here is 10. Yeah, I'm going to put something here. Hold on. And then I have a 3, and then a -1, and then a 10. So does everyone see that all that is just a different way of representing this system of equations? Yeah?
Yeah.
Okay, now, there are some little subtleties in here. We do, now, what I write in red here, you don't normally write, okay? We need to understand that this represents the coefficient on our x's, and this represents the coefficient on our y's. And this side over here is a number, right? This is what it's equal to. So I somehow need to let you know that there's like an equal sign in here. So what we do, different books do it different ways. Let's see, this one uses a line. They put a line right here. Some books, now I put that in black because that needs to be there. Some books do a dotted line, all right? But I'll go with what your book does, which is this. And this right here is called an augmented matrix. The augmented matrix, sound like metal on metal, no? Was that? Augmented matrix lets you, tells you that you have an equation. You have x, y equals a number, x, y equals a number. That's different than this. Let me just write this down over here. That's a matrix, isn't it? It's actually just this part of the matrix, isn't it? But that's not an augmented matrix because it does not include the equals stuff on the other side. So this is sometimes called like a coefficient matrix, but we're just going to leave this alone, all right? So we have an augmented matrix, right? Over there? Good? Now, how about the problem that we did before this? Here's another example. Where we had the system, the 3 equations, 3 unknowns. That big ugly one. Where was it? This one. 1, 1, -1, -1, 4, -3, 2, 16. 2, yeah, 2, -2, -3, 5. That's the problem that's the second problem we did today. Do you recognize the second problem we did today? You recognize that? It was x plus y minus z equals -1, 4x minus 3y plus 2z equals 16. And 2x minus 2y minus 3z equals 5. Yes? Okay. So these are 2 augmented matrices. So let's look at that one right there. What would your goal be if we were trying to solve this? What was our goal before? Get these to be gone, right? And then get this to be gone. Yes? So our goal is to have something like this. And I don't know what these are going to be, so I'm just going to put little boxes here. Does everyone see that if we could somehow get this turned into that we would be able to back substitute and be done? Yes? So there are really zeros here. Remember earlier I said there were zeros, but now in a matrix, they are zeros. Yeah? So if there's nothing there, we'll just represent it with a 0. This is called